Okay, then let's continue. Who is now organizing this? Yes, just make it bigger, yeah. So yeah, today we are talking about marbles, and you know marbles here maybe from the ES203 field trip. You can see here on the island a lot of limestones, and you can also see a lot of calcites. Yeah, have you seen them during your ES206? Yeah. Yes. So and there you saw them also these dark layers in contact with very light layers, yeah, and that is because they contain different minerals of different chemical composition. So and here we have folded all these layers, yeah. So that means we had just compression from this side and this side, and then we have folded the layers. By the way, there is still these two tests missing.
Yeah.
Okay.
Anyone here who has not handed in the test? Anyone?
Moment, because that is important, because otherwise I'm getting here problem with the faculty. So let us just wait till it is open. So here we have then such a marble sequence, a strongly folded sequence. So those sequences which you have seen in during your ES106 field trip were not folded, they were actually layered horizontally. So and here we put in some pressure on it, or compression from the left and to the right, and then we are folding them. So and here the dark layer is dark because there is a dark mineral inside. And which mineral do you think can this be? Which makes such a layer then dark? So that is just a phlogopite-rich layer, and the phlogopite that is a biotite. So and maybe we have the phlogopite still here. So, but you know by now that the phlogopite that is a sheet silicate and that is dark. It is in the head space again, so that is not the one. It is a dark sheet silicate, and that makes this layer then dark. Yeah. So, but in general, such limestones they contain calcite, they can contain silica, and they can also contain dolomite. So, and I mean they contain the carbonate minerals, and I mean silica. So, and while you have been on your ES106 field trip, how have you tested if this is now these limestones which you check, if these limestones are silica-rich limestones, or if they are calcite-rich limestones? How you have tested this in the field? Yes. So and if it is Swissling with acid, then it is a calcite-rich. Yeah. So whereas if it is rich in silica, then it is calcite pure limestone and contains then more silica, that's all. So the next slide. So here we have some other field pictures. So this one, that is then just a dolomite here. So in the dolomite, or the mineral dolomite contains a calcium magnesium carbonate compared to the calcite, which is only a calcium carbonate. That means that this dolomite contains also additionally some magnesium. So yeah, here you have your dolomite, yeah, and that makes the layer from the last picture dark. So and here we have another mineral inside in our dolomite. We have the mineral tremolite inside, and the tremolite, you know this by now also from the practical, that is amphibole, and the dolomite contains also calcium and magnesium, that is Ca2, Mg5, Si8, O22, OH2 mineral. So when this tremolite is formed by decarbonatization from our dolomite. So, and you know by now we can have dehydration reactions, and we can have decarbonatization reactions, and we can have a combination of both of them. Therefore, it is always very important that you are aware of the chemical composition of these minerals, because then you can understand relationships very, very easily in the field. So, and here on the basement we have a gneiss, and the gneiss is the, such a marble or a limestone that is a sediment, yeah. So, and then the metamorphosed component, that is then a marble. So, and if it is underlined by gneisses, that means a gneiss that can be metamorphosed granitic rock, yeah. So, and most of these granitic rocks, they are have an igneous origin, yeah. That means the protolite was a magmatic rock, but you can have also paragneisses, and the paragneiss has also as an origin a granitic rock, but this granitic rock was formed by sediments. So, and that means this granitic rock, which formed the paragneiss, was formed by sediments which become molten, and then this melt was removed and it crystallized again. But the origin from this rock have been sediments. But it was also a melt before. So, and if we have the situation here that we have some gneisses, does now not matter if this have been of igneous source or a sedimentary source, and we have here these marbles. What do you think was the environment where this sequence has originally been formed? That was somewhere at the ocean floor. So, and then due to tectonic processes, it has been lifted up. So, and if you are going back to your ES106 field trip, or if you are looking forward for the ES203 field trip, then you can see that all these limestones here are also underlined by magmatic sequences. Here they are underlined by gabbros, by basalts, or sometimes also by tonalites. So, but if you are looking forward, maybe 50 million years, then we have calculated that the Fiji microplate will collide with Australia, and then you are deform them, and then you will also lift them up. You can lift them up, or they are becoming subducted. So, and that is then actually our rock cycle. So then we have here number B, that is homogeneous coarse-grained tremolite marble. That is actually the same. Here we have tremolite marble, here we have tremolite dolomite, and we have here more calcium inside, and here we have the more calcite inside instead of dolomite. But, and this is then in another complex. I mean, this complex is seen or is shown from the central Alp, where this complex is from the Kalodenites in Norway. But the original geodynamic setting where this was actually formed, that was all at the ocean floor. So next slide, please. So here we have now a more detailed picture, and we have here such a marble, a tremolite-bearing marble. I mean, we are calling this a tremolite marble, the matrix that is marble, yeah. So, and then you have some minerals inside, and the dominant mineral in this marble is the mineral tremolite, and therefore we are calling this a tremolite marble. So, but we have also some other minerals inside, as I told you before. In such a marble you can find a lot of calcite, and that you can prove with your acid. So, and if the rock is then swizzling, then you know it is calcite. So then you have here the mineral talc. You know the mineral talc by now, that is this very soft mineral with a hardness of 1. I showed it to you just last week in the hand specimen. It is very, very soft, and you can actually scratch it with your fingernail. So, and then we have here, we have the calcite marble, then we have here another mineral inside, and that is the mineral dolomite. So we have then here more dolomite inside, and then we are calling this is a dolomite marble. So, and if you are checking it, both the rock types here, the dolomite marble and the calcite marble, which one do you think is then swizzling more by using acid? That is the calcite marble, because the calcite marble has, compared to the dolomite marble, more CO2, CO3 groups inside. So, and this rock contains then a little bit quartz, which is actually chemically possible. So, next slide. So, and that is now the triangle which we are using to describe these marbles. So, we have on the other hand the mineral calcite inside, that is very important to the, for rocks which are swizzling very much. Then we have then here some dolomite inside, and here we have the brucite and the periclase. So, and here on top we have the quartz. So, if we are going from here to here on this slide, then your rock will swizzle always less and less and less. So, and then we can subdivide them in different fields. So they are here gray shaded, we have here, for example, in this field 2A, we have silica and we have calcite inside. Then we are calling them calc-silicate marbles. So in this field here, we are calling them dolomite marbles. So as I told you right now, a lot of times you can distinguish them from each other in the field by using the acid. One is Swissing more, the other one is Swissing less. So, but you can distinguish them in the field also by using another method. And which method is this then? I just told you that talc is the softest mineral. So, and to check this, if it is a calcite or a quartz, you can then also use your pocket knife, because quartz has a hardness of 7 and calcite has a hardness of 4. So that means with your pocket knife you can scratch the calcite very easily here, whereas you cannot scratch the quartz. So then the quartz is also enhanced basically, more shiny compared to the calcite, and it has the quartz is then also hexagonal, yeah. So therefore you need a hand lens, whereas the calcite is monocline, and the calcite has good developed cleavage. So next slide. No, we are keeping this slide. So therefore we can then construct different mineral reactions. We are using calcite, quartz, and a little bit magnesium. We can then form a diopside, yeah. You know, the diopside is the calcium magnesium Si2O6. Or if we have enough water available, we can then also form a tremolite, or we can form the mineral talc. So, but to form a mineral talc, we do not need any calcium, because the talc does not contain any calcium. Yeah? So yeah, next slide. So, and here we have then the different mineral chemical reactions. We can subdivide them in the upper limit of quartz, in the upper limit of talc, the upper limit of tremolite, upper limit of diopside, upper limit of antigorite. Yeah? We can also form there antigorite, and that you know by now, that is a serpentine. So, and we can subdivide them in the upper limit of dolomite, upper limit of brucite. So, and these are all reactions for dolomite-rich composition. So, we need them for to run this reaction. We need dolomite. So, and then we have here the quartz-rich compositions. Then we need here also quartz in excess. So, and therefore all this reaction, we need then the mineral quartz, that these minerals can take place. So, and there you have decarbonatization reactions, and here, for example, you have dehydration reactions. So, next slide. So, and we have, or we are dealing in this rock with mixed volatile reactions. So, and therefore we have in this phase diagram again on the y-axis, on the x-axis, we have the XCO2. So, and on this side we have an XCO2 of 0. That means we have an XH2O of what? That is then 1. Yeah. So here we have, if we have an xCO2 of 0, then we have an x water of 1. So and on this side we have an xCO2 of 1. That means we have an xH2O of 0. So and everywhere between, if we are going here to 0.5, xCO2 of 0.5, that means we have an xH2O of 0.5 as well. Yeah? Because this x should always give you, or will always give you, not should, a total of 1. Yeah? So, and if we have a very, very less CO2 available in our system and a lot of water, then we are running different mineral reactions compared to a fluid which is rich in CO2. So if we have a lot of CO2, if our fluid is dominated by CO2, then we are forming then minerals which contain carbonate, yeah? Like the dolomite and the calcite here. Here we have this quartz, calcite, dolomite marble. So if we have a fluid which is dominated by water, then we are forming minerals, water-bearing minerals. That means we have in these minerals an OH2 group, like we have here in the antigorite, the dioxide, and we are forming then even by a very, very low CO2 in the fluid, we are forming then some calcite. So, but if we have less CO2 available in our fluid, then we are forming only calcite in minor components, yeah? Then we have the other parameter, that is then the temperature. Here we have the temperature again, and here we have the pressure. So, and under different pressure and temperature conditions during metamorphism, we are forming then different minerals. For example, here at high temperatures, we have then the mineral forsterite inside in our marble. And you know the forsterite, that is an olivine, that is the Mg2SiO4. So, but for you now as an ES203 student, what you should learn from this diagram is that your mineral reaction during metamorphism are strongly controlled by the fluid composition. Yeah? When you have a fluid which is very rich in water, you are forming then minerals which contain OH or OH2, and the antigorite has an OH4. Yeah? So whereas if your fluid is dominated by CO2, then you are forming carbonates. Yeah? So and therefore you can then make first estimations in the field what composition or of what composition your fluid was, yeah? Also when you are walking around in the field and you can see formations of calcites on your rocks, then you know that was, this rock was affected by a calcium-rich fluid. Yeah, it's water. Nobody will poisoning me. For example, we will also go during our field trips. I'm not sure which one now by now, but I think I will do it with you in the third year. We are going, or we are visiting the Manua Nebu. And there I will show you all the hot springs. Here they have in Manua Nebu a lot of hot springs. And these hot springs one can actually use for geothermal power. And on some of these hot springs, you can then find calcite concretion or layers of calcite on your rocks. And then you know this water, which comes up with the hot spring, had also CO2 inside, because otherwise you will not form these calcite layers. So next slide. So, and as you have seen before, if you have a lot of CO2 in the system, then you can see, then you can form a lot of calcite. Whereas if you have volumetric, only a little bit CO2 in the system, then you are forming less calcite. So these are then all fluid-controlled mineral reactions. Here we have in this diagram on the x-axis, we have the temperature. Here we have the xCO2, that means here we have a water-rich fluid, here we have a CO2-rich fluid, and here we have the modal composition in volume percent. So if you have then a CO2-rich fluid, then you are forming here at temperature below 500 degrees Celsius a lot of dolomite, yeah, because the dolomite is a carbonate mineral. If your fluid contains less CO2 inside, then you are forming then more quartz here. And if your fluid is very rich in talc, in water, then you are forming here at temperatures, let us say around below 500 degrees Celsius, you are forming the talc. And if you are increasing the temperature, then you are forming the more tremolite, because the tremolite is stable at higher temperatures and will break down at about 650 degrees Celsius. Above 650 degrees Celsius, we are forming then here dioxide and later on forsterite. These are water and carbon CO2-free minerals, and then you are just releasing here the CO2 to the air. So, and that is always, if you are looking at these rocks, not only at these rocks, at every rock, yeah? And that does not matter if this is now a metamorphic rock or an inchless rock. You can identify different minerals inside, yeah? Just if you are looking for this, where is it? Tonalite, yeah, the tonalite is a granitic rock, which you can find here on the Fiji Islands, yeah, here we have the tonalite. And here, for example, we have a granite. So these are now not metamorphic rocks, these are inchless rocks, yeah, but both of them are granites, yeah. So when this granite has this pinkish minerals inside, and which mineral is this? That is the K-feldspar. So when this tonalite does not have the pinkish minerals inside, yeah, this what you can see on the surface, which is a little bit yellowish to orange. That is just because a lot of people had it now in their hands, yeah. So, but in this one we have the much less, or actually no K-feldspar inside, yeah. So, and why do you think you have here K-feldspar inside and here not? That is why you have crystallized the tonalite or the tonalitic melt you did not have in the melt before potassium. So if you do not have potassium inside, then you cannot form a K-feldspar, yeah? Whereas in your granitic melt, you have potassium inside, then you can form K-feldspar. So if you have a lot of potassium inside, then you can form more K-feldspar. If you have less potassium inside, then you are forming less K-feldspar. So, and that depends always on the source of your different, or on the reservoir of your different elements, which kind of minerals you are forming, because if you have certain minerals not available, certain elements not available, then you cannot form certain minerals because these elements are just not available. So that is the same for the fluid. If you have a lot of CO2 inside, you can form a lot of carbonate minerals or carbonate-bearing minerals, whereas if your fluid is dominated by water, then you are forming a lot of OH2-bearing minerals. That's all. Yes, next slide. So yeah, here we have another XCO2 diagram where we are forming different minerals. Here at a constant pressure of 100 millipascal, and here on the y-axis we have again the temperature. So and what you can see here again is that if your fluid is water-rich, you are forming water-bearing minerals. If your fluid is rich in calcite, then you are forming carbonate-bearing minerals. So now you have formed these minerals. So, but now you can just use the limestone here, which you have seen during your ES203 field trip. You can use this limestone, and then you are heating up this limestone. Yeah. Let us say there is a tonallitic intrusion. Yeah. So, and if there is a placement of such a tonallitic intrusion, then we are calling this, or you are calling this, what type of metamorphism? Then you are calling this a contact metamorphism, and the result is then a contact metamorphic rock. So, and if you are heating up this rock of about 800 or 550 degrees Celsius, yeah, just let us remain or stay in this diagram. You are heating up this rock which has before, which was formed by forsterite dioxide and calcite. You are going above this temperature. Then your carbonate calcite will break down, and the CO2 becomes then removed from the rock. So it is always a giving and taking. So next slide. So that is now not the XCO2, we have the activity of the CO2. The activity is then just the coefficient, how fast, or not how fast, yeah, how fast the reaction will take place. Here we have the temperature activity CO2 diagram for silicist dolomites. That means we have the dolomite which contains also quartz inside. So, but you can see the same situation like before. If the fluid is very rich in water, you are forming then no water, yes, a brucite. Brucite contains a lot of water. So, and if the fluid becomes more rich in CO2, you are forming the carbonates. So, and that is in a shallow level contact aureole, yeah? So that means if we are talking about the contact aureole, that is the same situation as I just have told you before. We have the intrusion of a granitic magma, for example, takes somewhere place and is heating up the whole stuff. Then we have here shallow level. That means shallow level. This contact metamorphic event has taken place very close to the Earth's surface, yeah? So, and that is now, if we are talking about shallow level intrusions and we are talking about deep situated intrusion, that is also a question of the pressure. Because the depth goes always with the pressure. And therefore you are forming then also different minerals. So you have the temperature, the pressure, and the fluid composition, which controls the formation of different minerals through space and time. So next slide. So and there we have another funny diagram, yeah, that is the same kind of diagram as I have shown you before, and therefore we must not discuss this diagram now in detail again. It is also the amount. If you have a lot of CO2 in the fluid, then you are forming a lot of carbonate minerals, whereas if your fluid is dominated by water, you are forming then a lot of hydrous minerals. So next slide. So here we have now some field maps. And that is such a field map where a granitic intrusion has been placed in a silicificated dolomite marble. So here we have the granite intrusion, and here we had before these former marbles, yeah. So and there we have the emplacement of this intrusion, which takes place at a certain temperature. Then you are heating up your surrounding marbles, yeah. You are heating up your surrounding marbles, and therefore different mineral reactions take place. So, and close to the intrusion, you have here periclast, then you have forsterite, then you have tremolite, and here you have talc. So, and can somebody explain why you have this sequence? At first, you have the periclast, then we are forming the forsterite, and then in the outermost places you are forming the tremolite, and here you are forming finally talc. So which mineral is formed at highest temperatures around the intrusion, and which mineral is formed from these minerals which are formed at lower temperatures? Yeah, the periclast is formed at higher temperatures, whereas the talc is formed at lowest temperatures. So, and the periclast and the forsterite, they are anhydrous minerals, whereas the tremolite and the talc, they have the OH2 inside. So why have these minerals at the, or how does it come that these minerals at the outermost rim are the hydrous minerals? Of course, they are formed at lower temperatures. Yeah, they formed at lower temperatures. But how does this water, or how do you form here these water-bearing minerals at the outermost rims? How is this related now to the intrusion? That is related in the following way, because if your intrusion takes place, and here such a granodiuretic intrusion has maybe, while it was placed 750 to 800 degrees Celsius, something like this, yeah, So and there it was a melt which was in place, yeah? So and then this melt is cooling down and crystallizing, yeah? So and at first in this melt you are crystallizing all the water-free minerals, yeah? And then it cools down, and then your melt becomes relatively enriched in water, and then at lower temperatures this water shoots out and form then here in the outermost rim the tremolite and the talc. So and that is also a feature what you can observe here in Fiji, and where do you think you can observe this feature? You can observe it in Fiji at a lot of places. You have an intrusion, and this it intruded somewhere, and then you have the formation of hydrous minerals in the outermost rims. We will do this in detail in ES203. ES203 is the applied geology class, as maybe somebody knows of you, knows this. So in applied geology we are talking about ore minerals, and which ore minerals you can find here on all these islands. You can find a few of them. For example, if we are going to Bauta, which mineral they are looking for there? That is gold. So and the gold is enriched in the late magmatic stage with the fluid, and then it shoots out with the fluid, yeah? So and then another mineral what they are looking here for, that is not only gold, and they are looking also for copper, they are looking for telluride, they are looking for silver. So and this is all these relationships of the formation. So and if you have here, let us say a pure calcite marble which does not contain any silica, and you have the emplacement of such a granitic body, then you can form also some other ore deposits for gemstones. So in which one is this? Yeah, you don't know this because I have not told you before. These are then the rubies. Yeah, you know the ruby and you know the sapphire. So when the rubies and the sapphires are always formed in these marbles while they became heated up from a magmatic source. So in these rubies and the sapphire, they are only formed in a calcite-rich marble which has no silica. Because if there is silica additionally inside, then you are forming not a ruby or a sapphire, then you are forming a kyanite or a silimanite. Because the ruby and the sapphire, that is a corundum, which is chemically Al2O3, and if you are adding to Al2O3 silica, then you have Al2SiO5, and then you have just a kyanite or a silimanite, but the kyanite and or the silimanite, they have no commercial value compared to the ruby or the sapphire, which is a real good gemstone, and you can sell for a lot of money. So, but that is so the geological situation. You have the emplacement of a granitic body or of an igneous source. You are heating up the surrounding marbles or dolomites, and then you can form there some some minerals which are formed during contact metamorphism. So next slide. So that we don't read again, next slide. Yes, that is something very nice. So here we have a conduct metamorphic event and fluid infiltration of the Devonian Mount Morrison. So we have here then again the whole rock. So and here we have, a granitic body which has intruded in such a calx plus quartzite-rich rocks. So and there you have then a reaction front, yeah? And the reaction front is taken place in the contact between your granitic body and your surrounding calcite and silica-rich marbles, yeah? So and here, for example, we have here again a granodiorite, yeah, that is just a sketch map. So and here, very close to the granodiorite, you are forming the mineral wollastonite, yeah. So in the wollastonite, that is actually a pyroxene with Ca2, Si2O6, yeah. It is in the pyroxene triangle just sitting at the top. You are forming there this pyroxene, yeah. So a little bit more far away, in these grayish areas, you are forming wollastonite and calcite plus quartz, yeah, because this combination contains then also some CO2 in the fluid, which becomes removed later from your granodioritic body. So when more far away, you have then only calcite and quartz. So in the calcite and quartz, we have then here and here. That is then the temperature was not high enough that you can form the wollastonite. So, but here we have now a next thing or next sign here inside. We have here this stripe. So, and these are faults, yeah. So, and why do you think this metamorphic rocks which you are forming around this granodioritic body, especially those ones which are containing the carbonate-bearing minerals, yeah, as here the wollastonite and calcite quartz marble, and here only the calcite and quartz marble. Why do you think this formation has taken place mainly around faults? That is because the fluid has just to travel somewhere. So, and if you have a fault, then it just goes along the fault, because that is the easiest way. So, if you are checking all the hot springs in Vanua Levu, then you can see they are all related along faults or joints. Yeah? So, and that is because there the hot water can just come up. So, and now the next question is to figure out when this fault has been formed. That could be why the granitic granodioritic body has taken place. Yeah, you have an upwelling, yeah, or it can, that is probably, yeah, or it can also be a former tectonic process. It cannot be a later tectonic process because, or a very, very later tectonic process, because then your granodioritic body has still cooled down and will not produce any fluid anymore. So, next slide. So So here again, to repeat, a temperature, pressure diagram, contact metamorphism takes always place at low temperatures, whereas regional metamorphism, and that is if you have a collision zone, that means a continent-continent collision, or if you have a subduction zone, that takes place at high pressures. And these rocks then are highly deformed, whereas contact metamorphic rocks not that much deformed because they have only become heated up. So next slide. Yes, these two diagrams showing then again how it is related with the XCO2 and the pressure for different bulk chemistries at a temperature of 600 degrees Celsius. Here we have can you just, so you do not have this, yeah? No, that idea, I cannot read this. So, but anyway, you have different, you have different, what? Ah, yes, that is great. So now we can just check the bulk chemistry. Here we have 2 silica, 2 magnesium, 3 calcium, and then 5 carbons. And in the upper diagram, we have the same bulk chemistry. We have the same bulk chemistry, the same pressure relationships, and the same temperatures, but we are forming different minerals. So, and there is something wrong. There is something wrong in the textbook. Because I mean at the same pressure, temperature relationships and the same XCO2 with the same bulk rock chemistry, then you should form everywhere the same minerals. So, but here we have now the situation for a certain given fluid composition. Yeah, let us just go below. Yes, we have here different fluid compositions. So, and here we have, let us just check here, XCO2 of 0.74, and let us go to the other diagram. Here we have also an X074, but we are forming different minerals by the same given bulk chemistry. We are forgetting this diagram. There's something wrong. I think what is wrong, that is here we should have another bulk rock chemistry to show that different minerals are strongly dependent on the different bulk chemical composition. Yeah. So therefore they have made this diagram, but this is from a textbook. And I know actually the author from the textbook because I was a student from the author, and there the author has done something wrong by copy and paste. Yeah, next slide. So, now how does it look like in a thin section? So, I mean, at first you are checking in the field your hand specimens, yeah? You are taking a hand specimen, so, and then you are checking if it is a calcite-dominated rock or a silica-dominated rock. That you are doing just with acid and with your knife, with the pocket knife. So, and then you are inspecting the rocks for some minerals. So, and if you have such a dolomite marble or calcite marble, here we have a dolomite marble was formed in a contact metamorphic event from the Bargal area in the Alps. I showed you before also maps from this area. So, and then you are forming you have dolomite, you have calcite inside, you have the spinel inside, a green spinel, and you have a clinohumid inside, that is this one. So, but the spinel you can also identify in the hand specimen because the spinel is not white, yeah? So, but later on you are checking this under the microscope, and then you can observe certain minerals under the microscope, and here we have this, we have also a chloride inside. This is actually a clinochlor, yeah. So, and then it is a Forsterate grade marble, and that was then affected by a fluid which was about 600 degrees hot. And of course, there you are forming the minerals which you can form at a temperature of 600 degrees Celsius. Next slide. So now we have here another sketch map. Here we have again the granodiorite. Then you are forming here phlogopite, you are forming dioxide, you are forming tremolite. So the phlogopite is an OH-bearing mineral, but the phlogopite, that is the magnesium-rich biotype that can be formed at temperature or can be stable at temperatures of up to 850 to 900 degrees Celsius. Yeah? So, and therefore, you can form this area where you have phlogopite in phlogopite inside, but to form the phlogopite, you need a fluid which is rich in what? Is it a water-rich bearing fluid or is it a CO2-rich bearing fluid? That is a water-rich bearing fluid. So, and then in this zone, in this zone D, you are forming also, yes, you have the phlogopite, you have some calcite inside, but only plus minus, and you have K-feldspar inside. So, and the phlogopite as well as the K-feldspar are potassium-bearing minerals. So where do you think does the potassium come from? I mean, if you are checking this dolomite formerly these limestones, there is no potassium inside, yeah? So that means the potassium must come from where? That comes from the intrusion. So, but now, how does the potassium came out from the intrusion? What is the transport media by such an intrusion has taken place to form these surrounding minerals? That is the fluid. So, and this fluid contains not only water and CO2, it is water and CO2 rich bearing fluid. You can also, or you will also transport some elements. So, and potassium is an element which is very, very mobile, yeah? So, and that means the potassium group elements, which we will also talk later about in detail, I mean next year, if I'm still here, they will then transport the potassium, and then you are forming in these marbles potassium-bearing minerals, yeah? So, and this situation that you are transporting some elements in the fluid, you can also observe here in Fiji. And where is this? I just told it to you before. That is in the gold mines and the copper mines, yeah, because the gold and the copper is not sitting in the surrounding rock areas. The gold is transported with the fluid by such a diuretic intrusion. Here in Fiji, we have the case that we have here diorite intrusions, which are related to form these ore deposits, and these elements has been transported with the fluid. So that is the economic aspect from this feature. So, and here, if you have here the phlogopipe, then the potassium was transported with the fluid. So, and of course, close to the intrusion, we have the more phlogopipe, because we will not transport these elements then so far. That is this and the next, because I mean they are very mobile, but they are not that mobile. And we have the temperature effect that the phlogopipe is formed at very high temperatures. So if we have in the outermost zones also, I mean in the zone A, we have also some phlogopipe and some K-feldspar inside, but much less K-feldspar in phlogopipe. So, but in this zone A, do you think is this phlogopipe more magnesium rich or more iron rich? We have done all these things. It is then a more iron rich phlogopipe or biotite, yeah, because the iron-rich biotite or the magnesium-rich phlogopipe or biotite is formed at higher temperatures, whereas the iron-rich biotite is formed at lower temperatures. Yeah, that is there the FM exchange. So next slide. That we don't need. Yeah, then we are done with this chapter. Okay, then Neil will not be in next week, so I will see you then on Wednesday and Thursday.